Hey guys, here we go for online lesson number 3 for our year-long college algebra. So I know we all just got the word that we're not coming back this school year. Um, don't know how you guys feel about that. I know I have certain feelings about it. I'd love to chat with you guys. Come on to the office hours, message me if you need some math help, or just want to chat about what's going on. Um, it's an interesting situation. So, starting from here on out is going to be some new stuff. So I'm assuming we'll need a little bit extra help for that. So just please reach out. Also, please let me know if something's not working as far as the online stuff goes, if the videos aren't working, if you need some more help or more practice, just please let me know. Um, Obviously, it's, a little new to all of us. So just let me know what you need. I'll continue making these as I'm able, and we'll see how far we can get. So let me try and get my pen working here. Sometimes it takes a couple seconds, or sometimes it zooms in. So pen. Let's see if I can get blue working. Nope. Let me try again. All right. So the new stuff that we didn't quite get to, which would have finished up this unit, is rational functions. So let's jump right into that. It'll be a little bit different than the review online lessons because obviously those were just practice problems, but this will be new stuff. So let's see how this goes. So first of all, what is a rational function or expression? So rational just means a fraction, and a function just means a fraction of functions. And so we've been doing polynomials a lot lately. So essentially, a rational function is a polynomial on top of a polynomial. Usually, what we're going to do is a quadratic over a quadratic. Whether that quadratic is in expanded form or factored form, usually, if it's given to you in factored form, that makes things a little bit easier. So it gives you a bit of a head start on stuff. Also, looking at this, that should be a 7 down there. I know it's blocked by my video. But these are both rational functions. They just looked a little bit different because one of them's factored, one's not. So largely what we're going to do with these is factor the top and bottom and see what we have. So let's take a look. So we have the domain of rational functions. This is something we did last semester. Anytime you have an equation that is a fraction, you have to worry about the bottom equaling 0. So another idea for domain is we talked about excluded values. So an excluded value is whatever makes the bottom equal 0. So if we take a look at this, it's pretty obvious that -4 would make the bottom equal 0. So the domain of this rational function is all real numbers, so /r, except x cannot equal -4. So it's always all real numbers, except for the excluded values. So like I said, it's something we've done before. Sometimes you may have to factor the bottom to make sure, but it's all real numbers except for the excluded values. In this case is -4. Okay, so that's domain. Pretty simple. You don't have to worry about the top at all. So let's take a look at this. What is the domain of the rational function below? So if it's not completely obvious, there's a couple things you can do. First thing, in pretty much every one we do, is we could factor it. So 7, 14, we could factor that into 7x minus 2. Therefore, x cannot equal 2 because 2 would make it equal 0. Or we could set the bottom equal to 0, solve for x, and get 2 as well. But either way, the idea is that the domain is all real numbers except x cannot equal 2. So one of the main issues that people usually have with this is they want to say the domain is the excluded values. The domain is everything else. The domain is an infinite number of numbers except for x cannot equal 2. And so don't say the domain is 2. The domain is everything but 2. Little difference, but it matters. All right, let's see what else we want to do with the rational functions. So we want to classify those restrictions. Depending on how the rational function works, it might be what's called a removable discontinuity, which an easier word is a hole in the graph, or it might be what's called a vertical asymptote. So it's one or the other. So removable discontinuities that can be factored and canceled and show up as a hole in the graph. So it's a removable discontinuity if it can be factored and canceled and it shows up as a hole. So factored and canceled, we'll look at some of those examples of what that looks like. But it basically means you can factor it, you can cancel it top and bottom. Okay, kind of makes sense. It's a vertical asymptote if it cannot be factored and canceled. So if it cannot go away, it's an asymptote. And remember, an asymptote is an invisible vertical line that a graph gets infinitely close to but never touches. So we'll look at that more in the next lesson when we graph these. But it's either a hole or an asymptote, vertical asymptote. So in this last example, if I factor this, that problem turns into, and I can't cancel it. So it wound up being a vertical asymptote. If it can cancel, it should be pretty obvious. The top is just a 3 that can't factor, so I won't be able to factor an x minus 2 out of it. So it's just a vertical asymptote. So let's take a look at this one. Find the domain of a rational function below and classify its restrictions and find the zeros. So a lot to do here. I'll try and fit it in the margins. So the first thing is factor the top and bottom. Okay, with all of these, if you factor the top and bottom, so let's see, x plus 3, x plus 2 gives us the top. Okay, it multiplies to be 6, adds to make 5, so 3 and 2. The bottom multiplies to make negative 6, adds to make negative 1, is x minus 3, x plus 2. So the domain we're going to do first. The domain is all real numbers still except x cannot equal positive 3 and negative 2. Okay, it's whatever makes the bottom equal 0, and we've been factoring and solving for months. So x minus 3, x plus 2 means positive 3, negative 2. Now, that's the domain. Let's classify. So if we take a look here, we have an x plus 2 and an x plus 2 on the top and bottom. That means this negative 2, it came from the x plus 2, is a hole. If it can factor and cancel, it's a hole. The positive 3 factor did not cancel, so it's a vertical asymptote. So if it cannot factor and cancel, it's an asymptote. If it can, it's a hole. And these words will make more sense when we do some graphing because obviously they look a little bit different. So, yeah. Now, we did the domain, we classified, now we still need to find the zeros. Now, you should do these things in this order. Domain, classify, find the zeros. Because finding the zeros, you only have to worry about what's on top of what's left after what's been canceled. So the zeros is only negative 3. Because that's all that's left. Okay, it's all that's left after it's been canceled. -3 would make the top equal 0. We don't care about the bottom. We don't want the bottom of a fraction being 0. We want the top being 0. So zeros is only -3. So that's essentially what we're doing with this lesson is can you factor, can you cancel, domain, classify, zeros, stuff like that. One last thing is horizontal asymptotes. This seems like a lot, sorry, but it's just a three-case system. So we have three situations, and that'll determine our horizontal asymptote. And all you have to worry about is the degree of the polynomial on the top and bottom. So first case, if the numerator's degree is higher than the denominator's, then there are not any horizontal asymptotes. If the denominator's degree is higher than the numerator's, then the horizontal asymptote is 0. If the degrees are equal, then the horizontal asymptote is found by making a fraction of the two leading coefficients. So let me show an example about how this is pretty trivial, even though it seems unnecessarily difficult in terms of how it's written. So let's say I have 4x to the 5 plus 6x squared minus 3x to the 1 plus 4 over 6x to the 5 plus 2x to 3 minus 8. So something weird like this. All you have to worry about is the highest exponents, and in this case the degrees are equal. So if the degrees are equal, then we make a fraction of the two leading coefficients. So in this case the horizontal asymptote is 4/6 or 2/3. Okay, I care about nothing else with the horizontal asymptote. I don't need to factor it, I don't need to cancel. That's all it is. Okay, and once again, when we graph these in the next lesson, hopefully it makes a little more sense. Okay, but horizontal asymptote is just 2/3. Another quick example, let's say I have 5x to the 8 plus 2x squared minus 7 over 2x to the 4 plus 6x minus 1. Okay, look at the degree. All we care about is the highest exponents. In this case, the numerator's degree is higher than the denominator's, so there are not any horizontal asymptotes. So in this case, horizontal asymptotes don't exist. Okay, sometimes they exist, sometimes they're 0, sometimes they don't exist. So it's only the highest degree x. Okay, so let's throw it all together for a couple problems. I'll do the first, you try the second. Okay, so the domain, classify the restrictions, and find the horizontal asymptote. So of the first one, let's see, the domain, well, if I'm unsure, I can set the bottom equal to 0. And I see an issue. That's an imaginary number. There are no zeros on the bottom. So the domain is all real numbers because there are no restrictions. There's nothing that makes the bottom equal 0. There's nothing to classify. Okay. So the horizontal asymptote is 0 because the highest degrees, the degree on the top is 1, degree on the bottom is 2. And looking back over here, that's the example we did not do yet. If the denominator's degree is higher than the numerator's, then the horizontal asymptote is going to be 0. So it's 0. So in this problem, that's all we had to do. Okay. And this next problem, I'll give you a couple hints. The bottom can be factored. That is a difference of squares, x plus 1. x minus 1. Um, so domain, you should be able to get pretty easy from that. Nothing will cancel. There are no holes. There's vertical asymptotes, horizontal asymptotes. So you should be able to take it from there. So see what you can do with these practice problems with the Schoology quiz for the rational functions. The next lesson will be graphing them. So I'll see you on the other side, and hope you're staying safe and staying indoors like the rest of us. So see you later.